Welcome back. This is part 3 of the statics review. In this video, we're going to look at a simple truss and evaluate the internal forces in each member of the truss. The consideration of static determinacy in a truss is largely beyond the scope of this course. However, for a simple truss like this, we can see by inspection that it is statically determinate. There are 3 unknown external reactions, and we can easily evaluate the forces in each of the members if we know the external reactions. So I will start by drawing a free body diagram of the system right next to the original over here. I'm going to label the points A, B, C, draw in the 18 kip load, as well as each of my external reactions. Okay, so this time I'm going to determine the signs by inspection. I can see that A sub x will be acting to the left to balance out the load that's acting to the right. Okay, I can also see that A sub y will be acting downward because it's going to balance the moment about point B due to the load. If A sub y acts downward, B sub y must act upward. In the interest of time, I'm not going to solve for the reactions, but just state them. So A sub x is 18 kips, A sub y is 21.6 kips acting downward, B sub y is 21.6 kips acting upward. If you have the time and you want to practice, you're encouraged to try to solve for those reactions yourself. Next, we look at the forces in the internal members, AB, AC, and BC. One method to solve for those forces is to apply the method of joints, which basically allows us to do equilibrium of a joint to determine the unknown forces of the members framing into that joint. Method of joints is one of the 2 common methods for analyzing trusses, the other being the method of sections. Let's apply the method of joints at joint A, which requires us to draw a free body diagram of joint A and all the reactions or unknown internal forces of the members framing into that joint. We have the 18 kip reaction acting to the left, the 21.6 kip reaction acting downward, and then we have the 2 unknown forces, force in member AC, which I'll draw outward. That means I'm assuming it's acting in tension. And I have the force in member AB, also drawing it outward, the assumption being tension. By geometry, I can see the relative components of the force FAC. The height is equal to 6. The length is equal to 8, and I recognize this is a 3, 4, 5 triangle, so I know the length of the diagonal must be equal to 10. And that will help me easily decompose the components of that force. Okay, let's start with some of the forces in y equal to 0, since that will allow us to directly solve for FAC. Some of the forces in y, we have 6/10 of FAC minus 21.6 kips acting downward. Set that equal to 0. Solve for FAC. 21.6 kips divided by 0.6 or 6/10, and that gives us 36 kips. It's positive, so we know that it is indeed tension. Okay, now to solve for FAB, let's apply some of the forces in x equal to 0. What do we know? We have FAB, we have 8/10 of the unknown of the force FAC, which we now know to be 36 kips, and we have minus 18 kips acting leftward. Set that equal to 0. FAB equals negative 8/10 of 36 kips plus 18 kips, and this result turns out to be negative 10.8 kips. The negative sign, of course, tells me that the actual force FAB is acting in the opposite direction and therefore is in compression. Okay, again, circle my answer. I also like to sort of draw my answers on my free body diagram as I go and keep track of the information I'm finding out. So I have the 36 kips in tension, 10.8 kips in compression. Now the last unknown would be member BC. So in order to solve this one, we might want to draw a free body diagram of joint B. At joint B, we have B sub y, 21.6 kips. We now know the force in member AB because it's in compression. I'll draw it inward toward the joint, and I'm sorry, this is a known 10.8 kips. And then finally we have the force in member BC. I can see that it acts in compression, but just for the heck of it, I'll go ahead and draw it outward in tension. Some people like to always assume tension and then have the signs drop out. Okay. The geometry of this, the x component is 3, the y component is 6, based on the geometry of the truss. We could solve for the length in that member, length of the diagonal, which would be 6.71 from square root of some squares, or however you might approach it. So based on that, we could do some of the forces in x or some of the forces in y. I'll go ahead and do some of the forces in y. Equal to 0. So I have 6 over 6.71. FBC is the component of FBC in the y direction, plus 21.6 kips equal to 0. So FBC equals negative 21.6 kips times 6.71 over 6, which gives me an answer of 24.2 kips. And that also tells me that this force is actually compressive force. Okay? So I would draw my answer back in here, 24.2 kips in compression. Now again, I like to do a quick logic check. All my answers are in the right units of kips, which are force. If I look at joint C, which I did not consider equilibrium, but just for a logic check, that applied force of 18 kips, at joint C is balanced by 36 kips in the diagonal. But then to balance that force in the y direction, we get a compressive force of 24.2 kips in member BC. And just by quick inspection, equilibrium of that joint seems also to be satisfied. So it seems that the answer looks good.